Hello, I am Ihab Asad, and today I will present our work titled Gradient Extrapolation for Debiased Representation Learning, which was done together with Maha Shadaide and Joachim Denzler at Computer Vision Group Jena and accepted at ICCV 2025. Spurious correlations are unintended associations between non-causal features and labels. Models trained with empirical risk minimization often exploit these correlations when they are prevalent and easier to learn than the causal features. This leads to biased predictions and poor generalization, especially when these correlations are absent in the test set. A classical example is the water bird classification task, where the goal is to classify an image as either a water bird or a land bird. In this dataset, most water birds appear on water background, while most land birds appear on land background. ERM trained models can easily exploit this shortcut, learning to classify birds based on the background rather than the bird's features. As a result, it fails to generalize to test samples where the background label relationship breaks down, for example, water birds on land. Despite extensive research, existing debiasing methods still struggle on highly biased dataset. This motivates our work. We aim to develop an approach that is more general and effective, one that promotes causal relationships and helps models avoid spurious correlation. In this work, we propose GERNE, which stands for Gradient Extrapolation for Debiased Representation Learning. The core idea is simple. For each model parameters update, we sample two batches with different levels of spurious correlation, a biased batch denoted BB and a less biased batch denoted BLB, as shown in the middle subfigure. For both batches, we sample classes uniformly to keep class balance. The biased batch reflects the dataset's inherent bias, meaning it preserves the dataset's conditional attribute distribution. The less biased batch, on the other hand, has a more balanced distribution. We obtain it by interpolating between the biased attribute distribution PB and a uniform distribution of attributes, using an interpolation factor C, which we refer to as the bias reduction factor. We then compute the loss of each batch and their corresponding gradients. The difference between these gradients capture a debiasing direction shown as the red arrow in the right subfigure. GERNE then linearly extrapolate the gradients toward the batch with fewer spurious correlations to form a target gradient, which, controlled by an extrapolation factor beta, is used to update the model parameters. We can express the extrapolated conditional attribute distribution as a function of the extrapolation factor beta and the bias reduction factor C, as shown here. This equation reveals that GERNE forms a general framework for debiasing. When beta equal -1, GERNE reduces to standard empirical risk minimization in terms of the expected loss. When C equal 1 and beta equal 0, GERNE becomes equivalent to resampling, where we sample groups equally. When the product of C and beta plus 1 is 1, GERNE corresponds to resampling in loss expectation, but with the flexibility to control the loss variance through C and the amount of shared samples between the biased and the less biased batches. Finally, when the product exceeds 1, GERNE is equivalent to oversampling the minority groups. This equation also helps finding the upper and lower bounds of the extrapolation factor beta by bounding this conditional attribute distribution between 0 and 1 for all groups. Next, we explore the connection between the extrapolation factor beta and maximizing the worst group accuracy. Maximizing the worst group accuracy is equivalent to minimizing the maximum risk across all groups. We can show that the target loss in GERNE can be expressed as a function of the extrapolated conditional attribute distribution and the group risks, where each group risk's LG is weighted by its corresponding conditional attribute distribution. Since minority or underrepresented groups typically express higher risks, mainly because the model sees fewer samples from these groups during training, increasing beta effectively avoids their losses relative to the majority group. GERNE can be also extended to handle unknown attributes. Following previous work, we train a biased predictor and use it to predict the attributes. We then apply GERNE in the non-attribute case. To validate GERNE, we evaluate it on 5 vision benchmarks and 1 NLP benchmark, considering both cases where the spurious attributes are known and unknown. We begin with evaluating GERNE without any data augmentation on colored MNIST, corrupted cipher 10, and BFF-HQ. For colored MNIST and corrupted cipher 10, the evaluation metric is the average accuracy of a balanced test set. For BFF-HQ, the evaluation metric is the accuracy on the minority group. As shown in this table, GERNE consistently matches or outperforms the baseline in both the known and unknown attribute settings. Next, we compare GERNE against state-of-the-art methods on Waterbird, CELIP-A, and civil comments, this time applying the same data augmentation strategies as in the baselines. Here, the evaluation metric is the worst group accuracy. Across these datasets, GERNE again achieves strong performance, demonstrating robustness under both vision and NLP benchmarks. To conclude, our method GERNE debiases models by extrapolating gradients from batches that differ in their level of spurious correlations and achieves state-of-the-art performance across a range of vision and NLP benchmarks. Future work will focus on dynamically adapting the extrapolation factor and refining the attribute estimation for unknown biases. For more information, please refer to our paper and visit our project page. Thank you.